Can you tell me your name? Okay. Alright, look, I'll check. See what I can do. Your case is in from which course would you swap? What's your situation? The same thing. What's your name? Okay. What's your situation? Yeah.
So I was away last lecture. I have like 2 working from that.
Oh yeah. Oh yeah. You should be able to find it on Moodle. Yeah.
Because like, there's nothing on Moodle.
Oh really? Oh. Oh okay. Because other people were able to find it. Yeah, it should be. Yeah. I think if you just log into Moodle.help. No, there's nothing to it.
Oh, thank God for that. Thanks so much.
Okay. So just a couple of things. I don't know. Oh, yes, the lab bookings. So we've got the lab bookings finalized. So as I mentioned before, there's not going to be any organized tutorials or labs for this course, but there will be regular quizzes for you to go through to check that you understand the material and exercises. And there'll be labs every week that are optional, but we'll have consultants there who you can go and talk to. So the first couple of weeks, we haven't got any assignments out yet. We hope to have the first assignment released next Monday. But in the meantime, they may help you if you want to try to install TensorFlow on your laptop. I'll say a little bit more about TensorFlow later on in this lecture. Or if you want help with the quizzes and the exercises. And so these are the times that we've selected. We tried to find times that you are mostly free, and we have these labs. Booked now, so be aware of that. Now, so I'll just Today we'll move on to backpropagation. Along the way, I'll revise a little bit about perceptrons that we were talking about last week. So we'll talk about the basic backpropagation, and then we'll talk a little bit about variations on backpropagation. So, okay, so let's first talk a little bit about supervised learning and Occam's razor and multi-layer networks, and then we'll talk about gradient descent. So there's kind of three types of learning that we'll be talking about in this course: supervised learning, reinforcement learning, and unsupervised learning. So supervised learning is where a learning system is presented with pairs of inputs and outputs. Here's an input, and this is the corresponding output. So you have a list of inputs and outputs. And then from that it's supposed to learn a kind of function from inputs to outputs. So then if you then presented with some new inputs which are not among the inputs that you gave it, but it's similar ones, then it should be able to try to guess what the correct output is for that input. Then we have what's called reinforcement learning. So reinforcement learning, this is used when an agent tries to learn to play a game or act in an environment or allocate resources in real time. And sometimes for some of these tasks, it's difficult to provide an actual training set of inputs and outputs. So with reinforcement learning, the agent is not presented with actual outputs, but it simply acts in an environment and makes decisions, and then it's given a reward signal. So the reward signal tries to indicate how well it's doing at performing the task. So this is a little bit like that sort of game, those games that children play of Blind Man's Buff or Marco Polo, where someone's blindfolded and is wandering around trying to find something, and the other children say whether they're getting warmer or colder, whether they're getting closer to the thing that they're looking for. So you're not told the real answer, but you're sort of told how good your answer is. And finally, there's something called unsupervised learning. In this case, the agent is presented only with the inputs themselves, not with any target output, and the aim is to find some structure in those inputs. So we'll talk about this in the last section of the course. This has a number of different applications. It can be used for generative purposes. Maybe you're given some images, and then this will help you to produce new images which are in a similar style. It can also, unsupervised learning can also be used as a kind of preliminary step towards supervised learning. And there are sort of combinations. There's something called semi-supervised learning, which is a combination of supervised and unsupervised. Okay, but so we'll get onto these later in the course, but for the early part of the course, we're going to be concentrating on supervised learning. Okay, so with supervised learning, we have a training set and a test set, each consisting of a set of items. And the input is, traditionally the input was presented as a number of sort of, a set of numbers that are sometimes called input features, and the target is either a value or sometimes a multi-dimensional value. So it could be one target value, one number that you're trying to predict, or several numbers that you're trying to predict. And so you have like a certain number of inputs. This input has a certain number of components, and so does the output. And there's always this distinction between the training set and the test set. So the idea is you're not just memorizing. If the task was just to memorize the training data, then all you'd have to do is store them in memory. And then when you're asked to recall, you just look for that particular training item and pull out the stored answer. But actually, what we want to do is kind of generalize the pattern of the outputs to new kind of unseen data. So we always have this distinction between training data and test data. Now, there's a lot of different learning paradigms available. Those of you who took the machine learning course will be familiar with this. In this course, obviously, we're going to be concentrating on neural networks, but there's also decision trees, support vector machines, k-nearest neighbor, naive Bayes, and so on. So there's a whole kind of group of these, but neural networks tend to be the ones that at the moment are producing very good results in a lot of cases. So if you want to do some supervised learning, there are various decisions you have to make along the way. So you have to, the first thing is to decide what framework you're going to use. And then a representation. So sometimes you have a choice of how you're going to represent the inputs and how you're going to represent the outputs. Sometimes you need to do some pre-processing of the input. So if you're trying to process speech, sometimes there's pre-processing where you chop the speech into little time intervals and then you extract out, you use the discrete cosine transform to extract out different frequencies in the signal in that little piece, and then sometimes that's what you present to your neural network rather than just the raw input. So often you have to do some pre-processing. And after you get the output, sometimes you have to do some post-processing on the output. Then you've got to choose a training method. So last week we talked about perceptron learning. Today we're going to talk about gradient descent and backpropagation. And there are other variations on these training methods. So there's, and in TensorFlow you'll see how you can choose between these. So there's variations on backpropagation, and then there's things like the atom optimizer and so on. So you've got to choose the training method. You've got to be careful about generalization and overfitting, which we'll talk about in a minute, and how to do evaluation. So normally we train on the training set, but then we're really interested in the error on the test set. But depending on the purpose of the network, you may want a completely different kind of evaluation. So if you're training a network to predict the stock market, let's say you're training a network to predict the stock market, you have various inputs which may be historical or recent stock prices, interest rates, exchange rates, and various other things like that. And then what you might be wanting to predict is whether and by how much a certain stock is going to go up or down on a particular day. So but ultimately, what really matters is not how well you predict the movement of the stock, but how much money you could make if you were trading on that prediction. So then you may want to evaluate this by setting up a sort of simulated trading scenario where you train your network on historical data, or you simulate it as if it were trading and figure out how much profit or loss it makes. So, there's different kinds of evaluation. Okay, so what do we mean by overfitting? Now, again, some of you may have seen these things before, but it's always helpful to revise it. So there are many situations. In this situation, this is just a one-dimensional problem. You've got one input and one output. And this is the kind of thing you might see if you do one of those physics experiments where you're dangling a pendulum and measuring how long it takes to swing, or you have a puck's moving on an air table and you measure the velocity compared to the distance, or various things like this. So there's a lot of different experiments you can do where you have an input and an output, and you can do various measurements and put a cross, for this input I got this output, and for this input I got this output, and so on. And then the question becomes, well, what would you predict if the input had some other value that didn't previously occur? What output would you predict? Okay, so we could assume that this is a straight line. We could assume that it's a parabola. We could have a higher order polynomial like this, or we could just have some crazy curve like this. So there's many different ways to draw a curve that goes through all of those points. So let's have a show of hands. Who thinks the straight line would be the best choice? A few people want the straight line. Who thinks the parabola? Okay, that's more popular. What about the fourth order curve? Not many people want that. How about the crazy one? Okay, most of you, this was the most popular choice, and the straight line was the second most popular. It's interesting no one went for the fourth order thing. Okay, so the people who went for the straight line, who went for the straight line? Why do you think the straight line is good?
Simple.
Because it's simple, yeah. Well, that's a good answer, I guess. Who went for the parabola? Why do you think the parabola is good? It fits the points better than the straight line, and it fits the most points. Okay, so it actually, that's interesting. So it fits these 5 points very well, doesn't it? But misses out on that one. Now, was there anyone who wanted the fourth order polynomial? No one. Yes. Why? It fits all the points, yeah? And I did see someone going for this. Maximum entropy. Okay, you like entropy. So we kind of have an intuitive feel that this crazy curve is not going to give very good predictions, but it does go through all the points. Okay, so this illustrates a principle known as Occam's razor. Well, maybe I'll just say a little bit more about this. So I think, okay, so the straight line is reliable. You're probably not going to go too far wrong with the straight line, but I would tend to think that the parabola is better than the straight line because it does fit the points very well. Now, the choice between the parabola and the quartic is sort of interesting. If we, it kind of, whether you choose this or this really depends on how confident you are in the data. So this point could be what we call an outlier, right? This, you notice how the parabola fits everything else nicely, and then this is kind of wonky. So that would lead us to suspect that maybe something really went wrong with this point. Maybe the equipment malfunctioned and gave a very wrong reading, or someone who was copying down the result, skipped a decimal place, or, it was meant to be 0.18. It was meant to be 1.8, but they wrote down 0.18 or something like that. So there's sort of two different kinds of error in a way. So there's error that's just caused by kind of noise in the measurement where things move a little bit off the line. And then there is sort of gross error. So I guess that's what this comes down to. If we choose the green line, what we're saying is, well, we really think that this is an outlier, so we're just going to cut it loose. If we choose the blue line, we're very, very sure that that point really is a genuine data point, and so we really want to try to include it. Okay. So now here's another. So that was in one dimension. Here's another. This is another example in 2 dimensions. So in this case, there's 2 independent variables, and then you're trying to classify training items into 2 classes. So the positive class is the crosses and the negative class is the zeros. And then the task here is to try to predict how new points would be classified. So again, we could use a straight line, in which case it's very simple, but we're getting some of these training data items wrong. At the other extreme, we could draw some very kind of windy curve that classifies all these training items correctly. Or we could kind of go somewhere in the middle. So this curve kind of makes a good compromise. So it's an issue about compromising between the simplicity of the model and how well it fits the data. So this thing fits the data reasonably well. It makes a couple of errors, but it's relatively simple. Now we call this Occam's razor. This was named after William of Ockham, who lived in the 14th century. And I don't think he invented this principle, but he popularized it. What he literally said is, he said, if you've got two theories which explain the data equally well, you should choose the simpler of the two theories. But in modern terms, we kind of we loosen that definition up a little bit, because it wouldn't be true to say that these classify the. If we look at the middle one and the one on the right, it wouldn't be accurate to say that they both explain the data equally well, because that one fits the data a little bit better, but this one is simpler. So in other words, we're going a bit beyond what William of Ockham really said. We're willing to accept a model that doesn't fit the data quite as well on the grounds that it's simpler, right? So there's this trade-off between the simplicity of the model and how well it fits the data. So we're always going to try to look for this kind of compromise. Now, just saying a little bit more about outliers. Again, some of you have seen this example before. This is a classic example of an outlier. This is from the 2000 presidential election in the United States. In Florida, this was one of the closest elections in history. Al Gore lost the election by 180 votes, so thereabouts. So this graph here shows what was predicted by election polling for how many votes. So there was this third-party candidate called Pat Buchanan, and this is the blue things indicate what was predicted for how many votes he would get in each county in Florida, and compared to how many votes he actually got. Sorry, this axis is the predicted number of votes, and this is the actual number of votes. And there was a particular county called Palm Beach where Pat Buchanan got 10 times as many votes as what was predicted. So this is a classic case of an outlier. And then you sort of look and say, well, maybe there's something unusual going on here, some other explanation. And the explanation is that the ballot in that particular county was drawn up in a confusing way, and some people, because candidates were listed on both sides. So some people who attempted to vote Democratic, because Democratic is the second choice, they punched out the second hole, but it turned out that actually they accidentally voted for Pat Buchanan. Yeah. Okay. So this is what we're going to be keeping in mind, is this trade-off. Okay. Now, I'd like to just go back to this these perceptrons again, so that we're all clear what we're talking about. So last time we did we looked at the AND function. We'll just work through a couple of similar examples here, we'll look at the OR function, which is quite similar. So let's see if I can get this to show on the screen. So again, we're looking at logical functions. Let's say this is x and y, and we're looking to compute the function x or y, and we treat 0 as false and 1 as true. So x or y means that's going to be true if either x or y is true. So there are 3 examples where this is true and only 1 example where it's false. So again, we play this game from last week. So we draw a line that's separate. So we try to draw a line that puts the black points on one side and the white points on the other. And what we're looking for, we're trying to find an equation of the form W0 plus W1x, sorry, let me call this x1 and x2. So I'm looking at x1 or x2. So W0 plus W1x1 plus W2 x2 greater than 0. So I want this inequality to be true, to hold for these black points, but not for the white point. Okay. So I draw a line with my ruler, and the slope is -1. The intercept here is 1/2. So the equation of this line is x2 is equal to m times x1 plus b. So that's minus x1 plus 1/2. Now I juggle this equation around. I put everything on the same side. I get x1 plus x2 minus 1/2 plus x1 plus x2 equals 0. That's the equality, that's the actual line, but then I have to decide which side of the line I'm looking at. So and it turns out these black points are, well, if I pick one point here like 1, 1, this is minus 1/2 plus 1, so that's bigger than 0. So the black points are the ones where this is bigger than 0, and the white point is where it's less than 0. And we can draw this as a little perceptron. We can sometimes draw it sideways. So we've got x1 and here's x2. So these weights are +1. And the bias is minus 1/2. And then we got this step function. So we often draw it like this, left to right. Sometimes we draw it the other way up. So that the inputs go in here and the output comes out there. It's exactly the same thing, just a different way around. Okay, so that's the OR function. Now, what would happen? Let's suppose we wanted. What would happen if we looked on the other side of the line? So let's say we negated all of these weights. So the other side of this equation would be where this sum is less than 0. Or we could alternatively just negate everything here and say that it's bigger than 0. So this is something that holds for the white points and not the black points. Less than. Right. Okay, so these two are the same. Where are we? This is true for the black points. this is the same, so it's also true for the black points. But then if I swap this and say, well, I'm interested in the points where this is bigger than 0, then this would be true for the white points and not the black points. I think, is that right? So if I negate all the numbers, then I get a different logical function which is not or sometimes we abbreviate this as nor, right? So the nor function would is true here and false here. So this is like the logical complement of that function. Is that right? Yeah, so if with these perceptrons, if I negate, because of this Heaviside function, if I negate the bias and negate these two weights, then I get the opposite function, if you like. So instead of x or x2 being true, I get this one where x1 nor x2 is true. Okay. Any questions about this? Yeah. So you can kind of imagine this on this diagram. So this is the AND function we looked at last week. This is the OR function. And then if I made this black and those things white, this would be NOR. Right. So then we were discussing about functions that are not linearly separable. So if the straight line exists that separates the white points from the black points, then I can create a perceptron. But this XOR function is kind of the simplest case of a function that can't be separated by a straight line. Yeah, so this is where exactly one of the two things is true, but not both. Right? So my favorite example of this is if you recognize this in sentences like the following. There are some languages, in some languages like Latin, they actually have a different word for this inclusive and exclusive or. In Latin, vel, the inclusive or is vel and the exclusive or is out. But in English, we only have one word and you have to interpret it from the context. So the inclusive or, if I say I'll see you at the party tonight or I'll see you in class tomorrow, we understand that's the inclusive or, because it could be that I'll see you in both places, right? But an example of the exclusive or is the following. Either you give me the money or I'll punch you in the face. Okay? That's the exclusive or, because we understand from the, if you gave me the money and I still punched you in the face, you would be surprised, right? You don't think that's going to happen. Okay, so that's this one here. That dot there is the one where I give you give me the money, but I still punch you in the face. So it's missing here. Right, so how do we deal with these things that are not linearly separable? Well, if we've given this as a logical expression, we can break it down into simpler terms which are linearly separable, right? So there's multiple ways of doing this, but this is one of them. So as I say, that this point here is x1 nor x2. That point there is where neither of them is true. This point here is x1 and x2. So I can express this by saying, well, I don't want this and I don't want this. I want everything else. So it's this nor this. Right? So that gives me the clue of how to build not a single perceptron, but a network of perceptrons, a multi-layer perceptron that will compute XOR because I know how to compute NOR and I know how to compute I know how to compute NOR and I know how to compute AND, so I can just, okay, I think there's a minus sign missing here, sorry. This is to do with the way the PDF has been rendered. I'll try to fix that up when I get back to my office. Yeah, sometimes things drop out with the rendering, but this is actually supposed to be minus 1.5. And this is supposed to be minus 1. Okay. But you get the idea. Okay, so I can build a neural network by hand if I know the logical function. But in a lot of practical situations, I don't know the logical function. I'm just given these data points, and they're not in 2 dimensions. They're in a much higher, 100 dimensions or so. Okay. So this was the point where neural networks kind of got stuck for many years because people didn't really know how to solve this problem. Okay. So now that's what we're going to talk about now is the solution to this problem. Okay. So in general, we can build a 2-layer neural networks. Right, so next week we're going to start talking about deeper networks, but for a long time neural networks were just often just limited to 2 layers. And so you have a number of inputs, which is usually specified by the problem, and then you choose a certain number of hidden units, and then you have an output unit. Right? So this was the traditional sort of typical neural network architecture, and it made things simple because all you sort of really only had to choose the number of hidden nodes, as well as the transfer function, right? So this is our architecture. So in this case, we have 2 hidden nodes, but we could have 4 or 8 or 10 or 20, and normally it's fully connected. So normally every input is connected to every hidden node, and every hidden node is connected to the output, and it's not drawn here, but every hidden and output node also has a bias value. And so this is the data for this XOR problem. There's only 4 training items. But this is the general situation is we have an architecture and we have some training data and we want to choose the weights of this network so that when we put each of these inputs in, we get out the correct output. Okay. Now let's write these equations. Now, so these are basically linear functions, but we've just introduced a few additional variables. So we've got x1 and x2. So this value here, u1, is a combination of it's a linear combination of x1 and x2 with its own bias, and this u2 has its own bias. So we say u1 is b1 plus w11 x1 plus w12 x2. And then we have, that's a linear function, and then we have this nonlinear activation function or transfer function. So traditionally with the perceptron, this was just this step function, but we'll talk in a minute about different types of activation functions. So this function here called g, and then we do a linear combination here. So S is equal to C plus V1 Y1 plus V2 Y2. and Z is going to be Z is the actual output, is the transfer function of S, and often these two are the same, but they could be different, these transfer functions. And so with this if we've got this network with 2 inputs and 2 hidden nodes, we have 9 weights to specify that network, right? So all of this is fixed, and then we just try to find values for these weights that will correctly classify these inputs. Now, okay, so there's a couple of new ideas introduced here. So the first thing is, well, we remember this is supervised learning. So for each input, we have a target output. Let's call that T. So I can say, well, for each input, I want to look at the actual output of the network minus the target value. And, well, sorry, maybe I should mention this first, is No, I'll talk about the cost function. Okay, so if the target value, this Z minus T is a measure of how inaccurate what mistakes the network is making, right? So if the target value is 0, for this particular input, the target value is 0. Then for that input, we want Z to be as close as possible to 0, right? So if the output is 0, then the Z minus T will be 0. If the output is 1, then the Z minus T will be 1. So this error function, if the output is just 0 or 1, this error function is simply counting how many training items we're classifying correctly or incorrectly. Why is it divided by 2? Well, the only reason it's divided by 2 is a mathematic. So what we want to do is we want to reduce the error as much as possible. We want to find the weights that will give us the smallest error. Now, dividing by 2 is just a mathematical convenience because we're going to be differentiating this. And when we differentiate Z minus T squared, we get 2 times Z minus T. And we don't want to keep carrying that factor of 2, so we write 1/2 to cancel it out. Yeah, so it's just kind of a trick. Okay, so we can think about this as a kind of error landscape. So we can think about this as if this, remember, we've got 9 weights that we can adjust. So it's like we're moving around in a 9-dimensional space. And for any particular set of weights, I can test these inputs and calculate this error function. So there'll be some places where the error is 0. There'll be some places where it's 1. Where it's 2, where it's 3, and where it's 4. And what I want to do is find the place where it's equal to 0. Now, the problem is, so the real key idea here is to change this transfer function. So the transfer function we originally looked at was a step function. If the linear combination was less than 0, the node outputs 0, and then if it was bigger than 0, it outputs 1. So you got this discontinuous change. Now, if you use this, if we have this discontinuous transfer function, then this we wouldn't get these smooth changes, we'd actually get sort of abrupt changes like what's shown here. So the thing would be, for certain weights, the error would be equal to 1, and then at some point it would suddenly drop to 0. And then at another point it might suddenly jump up to 2. So it would be like a sort of, staircase thing. And the trouble with that is that we don't really, if we make a small change to the weights, maybe nothing will happen to the error. We used to get 3 of them wrong, and we're still getting 3 of them wrong. So the key innovation was, someone said, well, instead of having this step function, I'm going to replace it with another function which looks similar but is kind of smooth, right? So normally, let's have a look at this function here that looks similar to a function that's 0 here and 1 here. This is the actual formula that's used for this function normally, 1 over 1 plus e to the minus s. If you graph this function, it actually looks like this. So if s is 0, you get 1 over 1 plus 1, that's a half. If s is very large, e to the minus s is nearly 0, so you get something close to 1 over 1. If s is large but negative, then you get something close to 0. Right? And it's not obvious from this. There's actually a symmetry here. If I rotated this function about that point, it's preserved. That's not really obvious from looking at this formula, but it's actually true. So by moving from this to this, then what's happening here is, so this is, remember, this is this function here, g, that's going from u1 to y1 and u2 to y2 and s to z. So now, as I change these weights, that z will actually change smoothly, right? Because this function here is smooth, this z will be a smooth function of the weights. So that changes my landscape into this kind of smooth. Instead of getting something that sort of looks like a blocky thing, I get something that looks smooth. And that allows me to use a method called gradient descent to find the weights. So what happens here is, well, this is my particular. So I start with a certain value for all the weights, and I calculate the error, and the error turns out to be this. Well, one thing I could do is just make a slight change to the weights and then recalculate the error and see whether it's bigger or smaller. That's called hill climbing. I randomly change the weights, and if the error gets reduced, I change the weights and keep going. But in fact, yes.
Sorry, what determines the value of epsilon?
What determines the value of epsilon? The sigmoid function. This number here, e. Sorry, good question. Okay, that e is actually the natural base of the natural logarithm, 2.71828. Yeah, I should have said. Yeah. So this is like a fixed scale. Good question. Okay, so yes, sorry. So this is called a landscape. So, right, so I'm moving around on this landscape, and I think about it as if like I'm blindfolded, but I can take a step. When I take a step, it means that I'm making a small change to the weights. And then I can tell, and then you think about this error as like the height. So I'm trying to find the place where the error is as small as possible. So I could just sort of randomly try a step, okay, and see whether I go down or up. But in fact, I can do better than that because these functions are differentiable. So I can actually figure out, if I'm standing in a particular place on this landscape, I can actually figure out locally which direction I would want to step in order to go downhill as fast as possible. That's called the gradient of the gradient of the error. And so the way it works is as follows. Well, first of all, I note that I can differentiate this with respect to each of these weights, right? All these functions are differentiable. If you go back to your high school calculus, as I said, the derivative of E with respect to Z is 2 times Z minus T, but then the half cancels out the 2, so it's just Z minus T. And then the derivative of Z with respect to S, I can differentiate this function. And then I can differentiate S with respect to V1 is equal to Y1, and the derivative of S with respect to Y1 is V1. And then if I want to know the derivative of E with respect to W11, I can use the chain rule. I calculate the derivative of E with respect to this, and then the derivative of this with respect to this, and then the derivative of this with respect to this, and multiply them all together. So these computations are not hard, but they're just very, very tedious. Okay, so I can calculate the derivative of this error function with respect to each of those 9 weights, and I do that for each training item and add them all up, right? And then what I do is, let's say the partial derivative with respect to a particular weight W is written like this, dE by dW. Then I adjust that weight by subtracting, I pick a small number called the learning rate, and I subtract the learning rate multiplied by that partial derivative from that particular weight. So there's 2 ways to look at this. So one of this is the geometric way I mentioned. So if this does actually give, if I make a change to each weight proportional to the partial derivative with respect to that weight, that guarantees that I'm going downhill in the steepest downhill direction. Okay. Now, another way to think about this is to do with sensitivity. So if dE by dW is positive, that means this is the change in E with respect to the change in W for that particular W. So if dE by dW is positive, that means that increasing W in that direction will increase E, right? But I don't want to increase E, I want to decrease E. So that's why I have this minus sign here. If dE by dW is negative, then I want to increase W, right? So that tells you the sign. And then what about the magnitude? Well, if there's one particular weight for which dE by dW is very large, then you want to change that weight a lot because it's going to have a very big effect on E. If there's some weight for which dE by dW is very small, then I don't want to change that weight very much. And in fact, if dE by dW is 0, then I don't change that weight at all because it's not going to have any effect on E. So what this does is it changes each weight according to how big an effect it's going to have on the error, right? And I just want to change in a very small by a very small amount. So that might taking one step might move me from here to here, and then I repeat the process. Yeah, I change the weights from here to here, then I recalculate these partial derivatives at this point, and then I take another step, and I take these small steps, and hopefully I get down to a minimum now. But you can see there's a risk. This is called a local method because there's a risk I might get stuck in a local minimum instead of a global minimum. So there might be some point in this landscape where any nearby point has a higher error, but there may be some other point over here that does have a lower error. Right? So there's sort of a lot of discussion about this, but in practice, it turns out that in many practical problems with large numbers of weight, and in neural networks with large numbers of weights, it's actually unlikely that you get stuck in a local minimum. But theoretically, it could happen. So this is why we we have to adjust the learning rate appropriately. So if the learning rate is very small, we're going to move very, very slowly to get to the minimum. If the learning rate is too large, if the learning rate is really large, then it's possible we might overshoot the minimum and get onto this side, and then we might overshoot again, and the learning might become unstable, and we might actually the weights might just sort of bounce around and blow up. Right? So we've got to choose the learning rate appropriately. Yes? Yes? Oh, okay. The question was about sigmoid versus tanh. Now, next week we'll talk about some other activation functions, but these are the more traditional ones. Now, this function here is, so sometimes it's more convenient to have values between -1 and 1 instead of between 0 and 1. It doesn't matter that it's sort of more of a convenience and helps us to analyze the hidden unit dynamics. But if we want the values to be between -1 and 1, we often use what's called this hyperbolic tangent function. Now, which is defined this way, but it turns out that these two functions actually have exactly the same shape. It's just that one of them has been stretched. It's been moved down and stretched out and squashed up in the other direction. So there's been some rescaling, but the shape is actually the same. Yeah. And sometimes we use tanh at the hidden units and the sigmoid at the output units. It sort of depends on the application. But if it works one way, it'll probably work the other way as well. Okay, any other questions about this? Because I guess this is sort of a bit of a new concept to some of you. Yeah. Yes. The question was, instead of starting with a random set of weights, would it be better to start with the weights that that are at the global minimum? Well, okay, so it's a good question about how to choose. So, well, okay, there's a few, you raise a few different issues. So one issue is, well, how do you know? Often you don't know ahead of time which weights are going to form the global minimum, right? Ah, okay. Yeah, so that's very interesting. Okay, so you could differentiate it and set it to 0 and use high school mathematics. Yeah, that's okay. I didn't think about this. So for a small case, so for a case like this where we have 9 weights, sorry, the question was, could we just differentiate, yes, set the differential to 0 and then solve for the weights. Yeah, so if you have a case like this where there's only 9 weights, you could do that. That's a good point. Yeah, you could actually solve this analytically. Well, almost, actually. Actually, if you actually analyze this, there is no place. Okay, well, let me explore this a bit further. So, if we look at this particular data, well, let me put it this way. Have a look at this thing here. If the error was really 0, then the output of this function would have to be either 0 or 1. But the only place where it's 0 or 1 is actually infinity. So in this particular case, the minimum doesn't actually exist because the weights to make the error really 0, the weights would have to go to infinity. Now, they get very, very close to 0. If the weight size of the weights is like 4, it'll get very, very close to 0. Okay, so that's one issue. There may not be any minimum. But the more important issue is that you're solving simultaneous equations. So as soon as you get to a network of any kind of decent size, it's going to be too hard to solve those equations because it's not like a polynomial equation. It's an equation involving these tan h functions and so on, and then you won't be able to solve that analytically. Yeah, if you've got like 100 weights or 200 weights, it can't be done. Yeah, once you find the solution, you can verify that the derivative is 0 there. But it's just computationally infeasible to use that to find the solution. But it's a good suggestion, yeah. Now, to continue the idea of the weights, though, so one thing, if you where was I? Since you asked, I mean, I'm sorry the minus signs are missing here, but this is one solution, but there's actually, there's a lot of different solutions to this problem. You could negate, let's say, well, let's talk a little bit about symmetry. Sorry, where was I? If you have one solution to this problem, let's say you negate all the, let's say that this is, we're using tan h for the purpose of the argument. So if I made all of these negative and all of the, and this one negative, oh, well, I could swap I could swap these. It's an easier way to see it. So this could compute AND, this could compute NOR, and this could compute NOR. Now, alternatively, this node could compute NOR, and that node could compute AND, and that node could compute NOR. So there's multiple solutions. There's always multiple solutions that can be obtained by permuting the hidden nodes. And it's actually been shown that there's a certain kind of butterfly effect here, that if I start with certain initial, who was asking about the initial conditions? If I start with certain initial conditions, I may get to one solution. But if I change the initial conditions just a little bit, that might cause me to end up in a different solution. But in general, if you start with very small weights close to 0, that tends to improve your chances of reaching a global optimum. Yep. How do you check it's not a local minimum? I don't know. That's a good question. I mean, you could do random. The other thing is you could do random restarts. Like you could try training from different initial conditions and see whether you get a better answer. Sorry, did someone else have a? Yeah. You can do that. Yeah. I mean, there's no surefire way of telling whether you've reached the global optimum or not. Yeah, I don't know. You can sort of, for specific cases, you can try to make a guess, but there's no perfect way of doing it. Okay. Where are we? Okay. So this is just a few details about the derivative. So as I said, you could do this using the chain rule. Now, I'll talk a little bit about TensorFlow. One of the advantages of using something like TensorFlow is it actually does a lot of these, it does automatic differentiation for you. So you don't have to go through this tedious process of calculating the derivatives yourself. If you just specify the equations of the network, TensorFlow will automatically calculate the derivatives. So that's actually a big advantage. But if you were going to calculate them yourself, you would use the chain rule. And what about this activation function? Well, if I differentiate this, it turns out to be equal to this, and with tan h, it turns out to be this. But that's just, again, you can do this by just high school math. Now, why is it called backpropagation? Well, again, this is the equations for calculating z from x1 and x2. Now, when we calculate the derivatives, you work backwards. You calculate dE by dz, and then dz by ds, and then ds by dy1. And in practice, when you compute this, you need the derivative of z with respect, you need the derivative of e with respect to u1 in order to calculate the derivatives here and here. So if you write a program to calculate these derivatives, you have an array to store the derivatives of all the hidden nodes. Sorry, it might be better to look at it in terms of this picture. So you have an array. If you were going to write a C program or a Python program to do this, you would have an array to store these values, and you would calculate these values one by one and put them in an array, and then you'd calculate this. When you calculate the gradient, you have another array to store the differential. So you have an array here that will store the derivative of the error with respect to this and the derivative of the error with respect to this. You calculate those values and put them in an array, and then you use those stored derivatives to calculate these derivatives. So that's why it came to be known as backpropagation of differentials, because the way you implement the chain rule, you effectively the differentials get stored here and then reused, right? So sometimes we use the term backpropagation, but really that's just a way of calculating the partial derivatives. Okay, any questions about this? So this is, now again, I'm sort of going back to what traditionally was. So next week we're going to start to talk about image processing and multi-layer networks and that kind of thing, all the modern stuff. But in the old days when people only had two-layer networks, these were the kind of tasks they often applied neural networks to. Medical diagnosis, autonomous driving, financial prediction, and so on. So I'm just going to talk now a little bit about sort of techniques or tips, training tips that are used when we train these networks, because these principles are still relevant today. Okay, so this is an example of the kind of database, the kind of data that people would train a neural network on. So the Pima Indians diabetes data set. So this was a data set that was collected from, I think, a group of about 700 Pima Indians, several of whom had diabetes. So some of them had diabetes and some of them didn't, or later developed diabetes. And the task is that you're told various medical blood tests and so on that you can do. So someone comes in and you measure these various things, and then you have to try to predict whether that person is likely to develop diabetes or not. So the number of times the person has been pregnant, the concentration of plasma glucose in their blood, their diagnostic blood pressure, triceps skin fold thickness, 22-hour serum insulin. So a lot of these things are blood tests. Then there's the age. So there's like these 8 inputs, and then they're classified just as 0 or 1, whether they developed diabetes. So let's just talk. This is a useful example of some of the training tips that we would use. So in this case, we've got 8 inputs and 1 output. So if you had your neural network, you'd have 8 inputs, and you might have, let's say, you have to choose the number of hidden nodes. So you might have, say, 4 hidden nodes, and then you'd have an output. Now, you'll notice that these are all measuring things in different units. It turns out that this diagnostic blood pressure is measured in millimeters of mercury. The body mass index is measured in kilograms per meter squared. The age is measured in years. Now, if and from the data set that we have, this is the mean value in each of these and the standard deviation. Now, how should I put this? Let's suppose that so this triceps fold's thickness is measured in millimeters. Now, that's an arbitrary choice in a way. We could have measured it in centimeters. we could measure it in meters, we could measure it in micrometers, right? If this happened to be measured in micrometers, then every value would get multiplied by 1,000. So the mean would be 20,000 instead of 20. Now, the way this backpropagation works, so let's suppose that one value here, let's suppose all these other inputs have values that are in the range of like 0 to 100, but there's one particular value that's really, really large. This has values that are like 20,000. Well, what will happen is that the backpropagation will appear to be very sensitive to that input. Because this has been multiplied by 1,000, a small change in this input will cause a big change to these hidden nodes and a big change to the output. And so the gradient descent, the derivative with respect to that input will be very large, and the training will tend to change this value much more than the others, right? Now, conversely, if that value is measured in meters instead of millimeters, then the values would be really, really tiny, and so a change in the value would have very little effect on these values and very little effect on the output, right? So you kind of get this weird effect that if one input varies a lot, the network tends to, the inputs that vary a lot, their weights tend to change a lot, and the inputs that don't vary much, the weights tend not to change much. So there's this kind of distortion, and in order to get rid of that distortion, what we often do is rescale all the inputs so that they all have roughly the same scale. So it's sort of if you look at these standard deviations, they don't vary too much. But this one here varies by 115, and this varies by 0.3. So we probably want to kind of rescale this so that they have an equal effect. So often what we do is we rescale all we calculate the global mean, and we calculate the mean over all of the inputs of each, the mean over all samples of each input and the standard deviation, and then we often rescale these things so that everything has a mean of 0 and a standard deviation of 1. So this is just kind of a trick that often helps to make the learning more successful. Yes?
Does that mean you can arbitrarily multiply everything by 10 to get it closer to all the other variables?
You could. Well, if you multiply something by 10 and then you rescale, then it'll cancel it out. So, I mean, this is sort of an extreme measure in a way. It tries to make them as equal as possible. In practice, they don't really, it's really just, as long as they're not like massively disparate, it usually works out okay. Yeah. Now, another issue, we often have missing values. Sometimes, if you look at some of these classic data sets, sometimes a particular experiment wasn't done on a particular patient, so there's just a missing value. With neural networks, we kind of have to provide a value. We're not allowed, you can't get away with having something that's missing, so you have to sort of choose the mean of that value for everybody or something to plug that hole. As I said, initialize the weights to small random values, maybe of the size of 0.1 or something like that. And then there's different ways to prevent overfitting. Okay, where are we? 7:30. I think, yes.
Is it important to kind of consider a distribution of your inputs? Like, would we need to consider maybe doing like a log transform or a square root transform to force a certain distribution? Not force, but
Okay, the question was, should you do like a so this here is what we're talking about here is a linear rescaling. So you're saying, is it necessary to do a nonlinear, apply a nonlinear function to the inputs? That's not, I think that's not generally done. Usually well, that would be part of pre-processing, I guess. Yeah. I think it's not common, but there may be some situations where it is warranted. Yeah. I mean, if the input was a noise in decibels or something, in some sense it's already been transformed somehow. All right, I think we'll take a 5-minute break now, and then we'll come back and talk more about these tricks. Yeah.
question.
Yeah.
Like what's the point of having more hidden layers? Is it to make it more accurate or like?
So this is, well, I'll get to this next, but this is the issue of overfit. So having more layers makes it more, it's like equivalent to having more complicated function.
It's more like
right?
Like it's more generic to that data set.
That's right.
Okay,
so if you have too many hidden nodes, you may overfit. But if you don't have enough, then you may not
like
be adequate to.
not accurate enough.
That's right.
That makes
Yeah.
sense.
Why in the convolutional neural net we prefer to use rectified linear activation function instead of the sigmoid activation function?
Yeah. Well, it seems to work better in practice. There's still arguments about why. Yeah.
In fully connected hidden layer, we always use sigmoid better than
If it's a two-layer network, yeah.
and in the output layer, if we did not have a possibility, we will always use the softmax to write. Always softmax in the output layer will always outperform other activation functions. Is it the truth?
If it's a classification.
If they also have possibility.
If it's a multi-class classification. So we're getting an echo. Okay, so good questions. People raised some important issues in the break, and I'll try to cover all the things that were raised now in the discussion. So. So let's talk about this online versus batch learning. Okay, so you'll notice in the definition of this error function, there's a summation, and the summation is over the training items. So if we do, so one way to do this is we go through all the training items. Let's say we have 600 training items. We could go through all the training items. We could calculate this derivative for each of them and add them all up. Then we would get the true gradient for the combined error function. And we could update the weights, and then we could go back and recalculate for all those 600 training items. That's called batch learning. So we take all the training items as a batch. We use them to calculate the combined gradient, and then we update. Now, but in practice, we usually don't do that. In practice, what we often do is what's called online learning, which is sometimes referred to these days as stochastic gradient descent, or SGD. So the way stochastic gradient descent works is that we look at just one training input, and we calculate the error for that one input, and we calculate the gradient for that one input, and then we adjust the weights according to that input. So what's actually going on here is that, right, so we've got 600 inputs, but we're not actually calculating this combined gradient. What we're doing is we're calculating the gradient for training item 1, and moving the weights, and then we calculate it for training item 2 and move the weights. So we're actually kind of jiggling around in different directions, but the combined effect, when we've gone through all 600 training items, the combined effect should be to move us in that direction of the combined gradient. Now, there's two reasons why we normally do this. So one is to do with efficiency. If you've got a lot of training items, it can be very costly to calculate the gradient for all of them. And so if we just calculate them as we go, the thing may train faster. But the other thing is that it also, by doing the stochastic gradient descent on one item at a time, it actually corresponds to sort of adding a bit of noise. So the combined effect should be to move in this direction, but you're sort of bouncing around. It's adding a bit of noise to the process. And that noise often is actually helpful to us. It's sort of, it has the same kind of effect as simulated annealing, if you know what simulated annealing is, but a better way to think about it is that it can sort of shake us. If there's a small global minimum, maybe not a big global minimum like this, but if there's a little bump somewhere with a small local minimum, if we do batch learning, we might get stuck even in that small local minimum. But if we do online learning, because of the sort of noise and the randomness, it has a good chance of shaking us out of that local minimum and getting us down to the global minimum. Yeah, so the noise actually is often your friend. Okay, so that's the first point. I wanted to pick up on something. If you remember at the end of last week's lecture, I was talking about the credit assignment problem. So the reason that the perceptron learning algorithm with the step function doesn't work in this situation is because of credit assignment. So if this thing produces the wrong answer, it's hard to tell whether it was because of these weights or these weights or these weights. But this gradient descent, calculating the partial derivatives, you put in an input and you get a certain answer that's wrong. And what the partial derivatives is basically telling you that an adjustment to these weights is much more likely to change the output than these weights, right? So I make use of that information and I change these weights more than these weights, you know, or it may happen that a change in these weights will have a bigger effect than these or these. So that's the sort of the magic, if you want, of this gradient descent, is that in this particular situation it solves this credit assignment problem, and it directs the changes in the weights to the places where they're going to have the biggest, make the biggest difference. Yeah, it changes the weights that are going to make the biggest difference to the error and not the others. Okay, so online versus batch learning. And then the other question that a couple of people were asking me during the break is how to choose the number of hidden nodes. Or we can think about this in the more broad term of how to prevent overfitting. So if you remember, sorry to keep jumping around like this, but it's important to keep this in mind. So this straight line is effectively, we can think of as equivalent to a perceptron. And when we think about adjusting the number of hidden nodes in the network, we think about sort of choosing between this and this. So if we have very few hidden nodes, we think of that as implementing a simpler function. And if we have a lot of hidden nodes, we think of that as equivalent to having one of these very windy functions. So we want to choose a number of hidden nodes which is appropriate for the task, which is adequate to capture the properties of the training data, but not sufficiently powerful that it can overfit. So there's three. These are okay. So there's different ideas about overfitting. So the main way we avoid overfitting is by regulating the number of hidden nodes. Now there are some people who say they have a large number of nodes, but instead of limiting the number of nodes, they limit the training time. They say, well, I'm only going to train my network for a certain period of time. Now this is kind of controversial, but these pictures I'm showing here are meant to be indicative only, and what's shown here is the training time, but we could think of this also as the number of hidden nodes. You could think of this as being 5 hidden nodes, 10 hidden nodes, 15 hidden nodes, 20 hidden nodes. We would get the same kind of picture here. So what happens is, as you increase the number of hidden nodes, remember we have we often have a training set and a test set. So the training error will always go down as you increase the number of hidden nodes. But if you look at the error on the test set, what will usually happen is it'll go down for a while and then it'll kind of level off, and in some cases it may then start increasing, which is a sign, the fact that the training error is, that the test error is increasing while the training error is decreasing is a sign that we're overfitting, right? So in some situations it does sort of work to limit the number of training epochs or the number of weight updates, you know. So the idea is to try to stop at the point where the test error is minimized, right? So if this were really the number of training cycles, we'd say, okay, from looking at this graph, we'd say, okay, 10,000 training cycles is the optimum. We don't want to train longer than that because we'll be overfitting. If this is the number of hidden nodes, then whatever number of hidden nodes is here, we'd say that's what we choose, right? So it's really, there's no sort of theoretical way to choose the number of hidden nodes. It's usually done experimentally, but you do typically get this pattern. So any number of hidden nodes in this range would probably give the best generalization. Now, sometimes we talk about a validation set, so this is sort of terminology, but sometimes there's actually a test set that you really don't have access to. But you may chop off some of your training data and use it as a kind of validation set. That means you're pretending that it's a test set. You're not training on that data, but you're just using it for this purpose to try to see what the generalization is. So at the point where the error on the validation set starts to increase, you want to choose a value that before the error on the before the error on the validation set has started to increase. Yeah. Now again, okay, so there are some I guess the point of this is that there are some situations where stopping the training early really doesn't help you. You know, like you can safely keep training as long as you want and the validation error will still go down. But if we're talking about the number of hidden nodes, we almost always get this picture. It'll come down for a while, plateau, and then start increasing again. So often we just like try with different numbers of hidden nodes experimentally, and if it's a validation set, once we've decided, if it's a validation set, what often happens in practice is, let's say we have 1,000 training items to begin with, we use 800 of them for training and 200 for validation. And based on some experiments, we decide that the optimum number of hidden nodes is, let's say, 10. Well, then we retrain the network on the whole. We say, okay, we'll fix the number of hidden nodes at 10, and we'll retrain the network using all 1,000 training items, because that'll get us better. We want to use all the training items if we can. But it's still acceptable to do that because we haven't touched the test set yet. We've done all of this with the training set. Okay, so weight decay we'll talk about a bit later. Momentum we'll talk about a bit later. So, and the learning rate. So again, the learning rate we often have to tune by hand. You know, if the learning rate's very low, the network will learn, but the error will come down very, very slowly. At some point, if the learning rate becomes too big, the error may actually kind of blow up again or something. Yeah, the learning becomes unstable. Okay, any questions about this? Yeah.
Can you use a neural net to get the optimal
Can you use the question was, can you use a neural network to learn the optimal learning rate? I'm not sure. If you have enough different... I never thought about this. But each data set becomes one training item. You got to have enough. You could do it, I guess, but yeah, you would have to have enough training sets to provide enough data to train with. Yeah, I don't know. It's a good point. I think what you mean is there an automatic way of I'm not sure. There are actually hyperparameter. Okay, so there are these things called hyperparameter tuning algorithms. That so often you have multiple. You have not only the learning rate, but you also have these other things like weight decay and momentum. So you may have 3 or 5 hyperparameters. There are actually there's software you can get that will try. Yeah, you could just do it with trial and error, but if you try every combination, there could be if there's 5 of them and you want to try 5 values for each, then like you've got 625 different experiments. So there are some hyperparameter tuning algorithms which try to test them in a way that's a bit more intelligent. Like you try one set of values and then another set of values, and there is a kind of literature about this. Yeah, I mean, it's still fairly intensive, but it's more efficient than just trying every possibility. Yeah. Very good question. Okay, I think I'll defer this example until later when we talk about geometry. Sorry, maybe I'll say a little bit about this. This is just one example of neural networks from the old days. So this was very early work in autonomous driving in Pittsburgh in the 1990s. Autonomous driving has come a long way since then. But these guys, with using a 2-layer neural network, they were able to drive all the way from the east coast to the west coast of the United States with this kind of technology. The hard part was getting onto the freeway and then getting off the freeway at the other end. Once you're on the freeway, things are much simpler. But the system that these guys used in the early versions, they just had a camera mounted in front of the vehicle. Well, they had what we would call an SUV now, because they had, they needed the computer to get the compute power that they needed. They couldn't use a regular sedan. They had to use a big sort of semi-trailer kind of thing so they could fit these computers in the back. So they had a camera mounted on the front of the car, which was taking this image that was converted into a 30 by 32-bit image, pixel image. And then they had 4 hidden units, and you could. This is this issue about pre-processing and post-processing. So the aim here is to try to decide where to put the steering wheel. So in theory, you could just have one output, and the output tells you the angle to turn the steering wheel by. But they found it was a bit more safer or robust to have multiple outputs, and then each output corresponds to a particular angle of the steering wheel, and then they take a sort of weighted average of these outputs to determine the actual steering angle. And in the first experiment, they had 4 hidden units. Later on, they experimented with more hidden units, and they also had like a laser range, sonar rangefinder. But let's just look at the simplest system. So they had 4 hidden units and 30 outputs. Now, and they trained it on, initially they trained it on human data. So they got a human to drive the vehicle and made this huge log of input images. You know, so here's an input image, and here's the steering wheel that the human chose for that particular image. You know, and here's another image. So they just created this massive training set based on this, and then they used supervised learning. They had to eventually augment it as well with sort of synthetic data. Now, but part of the reason I'm showing you this is like it starts to give us an idea of how to visualize. Someone was asking in the break about what these hidden units actually are. You know, do they represent something meaningful, or are they just kind of some weird phantom thing? Now, one way to try to understand these hidden units is with what's called a Hinton diagram. So what this diagram here represents is one of these hidden units, and this here represents all the weights from the input to that one hidden unit, and this top row is the weights from that one hidden unit to all the outputs. And each weight, I think a white dot represents a positive value and a black dot represents a negative value, and the size of the dot represents the size of the weight, right? So this is a way of sort of visualizing these things. And so what this means is, so if this particular unit is active, it's very likely that the person would steer sharp left. That's what these top weights are telling us. There's a high likelihood that the person would steer sharply to the left, but there's some possibility they may also steer a soft right. You know. So, and if you look at this image here, well, I guess it doesn't. The point I'm making here is this: it doesn't always represent a particular scenario. Sometimes it represents a superposition of 2 or 3 different. Sometimes one hidden unit will represent a superposition of 2 or 3 different scenarios. So this unit will be very active if the road happens to occupy this part of the image, then that unit will be particularly active. But if the road occupies, you see there's white stuff over here as well, so if the road occupies this position, it would also be relatively active. So yeah, so it would be nice to think that each hidden unit corresponds to a very specific configuration of the road, but often it's like often there might be 2 different configurations of the road which both activate this unit, and then these other hidden units they'll be activated by certain other configurations, and then the output sort of sorts all of this out. So it's you sometimes get this kind of these funny kind of superpositions, but it does give you some way of visualizing what sort of inputs would activate that unit. Okay, any questions about this? Yeah. Yes?
Is the color representing the weight?
The color is representing the weights, yeah. So white is positive and black is negative. That's right. Yeah.
So would it be possible to initialize a neural network with a certain thought behind it? So having each, for this example,
Yeah.
each layer say, generally when the road is going this direction, I want the weights to suggest that you should turn sharp left. Or if the road's going that direction, turn sharp right, in the sense of showing that diagram, having maybe a curve going off that direction, and that should suggest a sharp left. Learn from there.
So the question was, could you like initialize the weights in a clever way? I think you possibly could. I mean, we'll look at more diagrams like this when we get to convolutional networks. But sometimes we use like unsupervised learning first to effectively to initialize those features and then use backpropagation afterwards to refine them. So that's probably sort of similar to what you're saying. Yeah.
So it's possible.
It is possible. Okay, I might, before we move, okay, so I'm going to move on to variations on backpropagation. We might not get through all of that today. We might leave some of it to next week. But I thought I might just say a little bit about TensorFlow while we're here. So because it does illustrate a few of the things that we've been talking about. Let me have a look here if I can switch to the laptop. Oh. Okay, so I just wanted to make a few, I just wanted to make a few remarks about this and then we'll provide more details along the way. So we've been through a bit of how should I put this? We've been through a bit of discussion about which version of TensorFlow to use. So these things are sort of rapidly changing, and the latest stable version of TensorFlow available at the moment is 1.9. Now, has anyone here installed TensorFlow on their own laptop, or a few of you have? What version did you install? 1.4? Okay, now what we're going to, for the most part, we're going to try to stick with syntax that's tradition. Like we're going to try to stick with syntax which works in all versions to the extent that we can. But part of the reason we want to use 1.9 is because this, the files, the older versions, when they save weight files and load them back in again, they're very, very big. They can be like 80 megabytes or something. So I think the later versions manage to save them in a more efficient way. Now the lab machines, I try not to bore you with too many details, but the machines in the lab, for some reason, they're running a 32, they are 64-bit machines, but they're running a 32-bit operating system, and so the latest version they've managed to get running natively on the lab machines is 1.3. But there's some emulator that you can run on the lab machines that will make them run in 64-bit mode. So there's going to be a few little technical details like this, and we'll put more details about this up on the website. So when you're in the lab, we expect, first of all, we expect most of you probably will be using your own computer, but if you don't have your own computer, well, you will be able to run the things on the lab machines using this emulator. And for the later assignments, there's also the option of using this Google Colabs and so on. But if you need to use the emulator only runs on the lab machines, it doesn't run on login. So if you SSH remotely into the CSE machines, you won't be able to use this emulator, but there's this thing called VLab, which would allow you to use it. Okay, so yeah, I apologize for all these kind of technicalities, but we're just trying to make sure that everybody has access to these right version of TensorFlow in one way or another. So there's this web page that describes let me see where it is. There's a web page that describes how to run this VLab. So basically, you have to, if you need to log in remotely and run this emulator, you have to install a VNC client. So I went through this process myself a few days ago. I found it's better to compile it from source rather than use a downloaded binary. And you also need to have a VPN in order to run this. So let me just quickly demonstrate that this works. So there's a VPN available from the school that you can use, but my preferred VPN is Lantern. It doesn't really matter which one you use, but so if I click on this, then it's now running this VPN. And then if I run VNC Viewer, this tells me that I'm going to connect into VLab. And then I just log in with my normal username and password. And then it's like a virtual machine. And I can open a terminal. And then the name of this emulator is Run64. So when I type that, then I can get access to the latest versions of TensorFlow. Okay. Now, I just wanted to, okay, so if you you should probably, if you've got your own laptop, you should probably try to install TensorFlow. So this is, you should install, as I said, 1.9. So if I go to TensorFlow.org, then there's instructions for how to install the latest version. So click on install, and there's all the instructions here. Now, if you have trouble, you can go along to these lab sessions and the consultants will be happy to help you out. But the other thing is that the newer versions of TensorFlow, often they build like highly abstracted layers on top, and we want to try as much as possible to kind of use the low-level commands rather than the high-level ones, because for the teaching purposes, some of these abstractions really kind of abstract away so much that it's hard for you to learn what's actually going on. So there's certain features in the modern versions that we'll be avoiding. So we're not going to use Keras in this course, and we're not going to use eager, and we're not going to use eager execution. We're just going to use more traditional stuff like tf.layers and tf.nn. Okay, so as I said, we'll put more details about this up on the web page, but I'm just kind of flagging it. So I've just gone back to, just to show you a very, very simple program in TensorFlow. I've gone back to one of the original tutorials from 1.1, and what this actually does is, just does a linear regression. So this is very, very simple. It gives you some data, and I think what it's trying to learn is just, if you can see what the data looks like, the x values are 1, 2, 3, and 4, and the y values are 0, -1, -2, and -3. So this is simply trying to learn the function y equals, someone tell me what the relationship is between y and x. Y equals -1 minus x. That's right. And this is the actual, this is the TensorFlow code. So it says import numpy, import as np, import TensorFlow as tf. So it's trying to learn. So effectively what it's trying to learn is y equals w times x plus b, and you're just trying to learn the values of w and b. So it's the simplest possible regression you could have, but it just shows you how the thing is set up. So it says, okay, w is a TensorFlow variable of type float32, and its initial value is 0.3, and b is the same thing, but this is its initial value is -0.3. And then it says that x and y are placeholders, and the linear model is w times x plus b, and then there's a loss function that's trying to reduce this sum, and the sum is the square of linear model minus y. So this is implementing the things we were just discussing in the lecture. This takes the output of the linear model minus the target value and squares it, and we're going to try to reduce this by gradient descent, and the learning rate's going to be 0.01, and then this specifies the training data for x and y, and then when you run this, it repeats this 1,000 times training this. So some of these things are built into TensorFlow, and then this evaluates the training accuracy and prints the result. Okay, so so what actually happens here is it creates a kind of computation graph. So W gets multiplied by X. The result gets added to B. So this is implementing the linear model. And then remember, Y is the target value. So the output of the model is Y is subtracted from the output of the linear model. That value is squared. And then something else happens to it and it gets summed up. And the gradient of all of these different things is calculated. So you specify these computations in the forward direction, and the TensorFlow automatically calculates the gradients for you and does the gradient descent. Yeah. So let me just see. I think I have. I've just copied and pasted that code in here, and if I say Python 3 train.py, it comes back and says, okay, W, what did we say? It should -1 and, it should be 1, that's funny. It should be, I guess it must be Y equals 1 minus X. So, yeah, B should be 1 and W should be -1. So it's gotten very, very close. And the loss function is something times 10 to the -11. Okay, so it's a obviously very simple example, but it's doing what it should. This is from a very old version of TensorFlow. So this would have run under the old version anyway, but it also runs under the new version, yeah, because it's a sort of common syntax. All right, any questions about that? Yes?
What is the main advantage of TensorFlow? The main advantage of TensorFlow?
As opposed to what? Scikit. Yeah, good question. So we've considered TensorFlow, PyTorch. I don't know. There's a few different frameworks out there that all do sort of similar things. Theano doesn't seem to be supported very much anymore. I think it's become sort of legacy. And TensorFlow was designed by people who previously worked on Theano, so it's kind of Theano plus. We feel that TensorFlow is kind of a standard. We did consider PyTorch. PyTorch seems a little bit more flexible in a way, but a bit more work to get into. So have you had a go with Scikit, or yeah, you think it's good? Yeah, I mean, all these things are quite similar. They all do similar things. So they have Python code which optimizes. So this can be run on a GPU. So if you can't get the GPU to work, if you can't get this to work on the GPU with your laptop, it's probably okay. But theoretically, you should be able to get a GPU. So, you know, they all have sort of code in there which figures out what the best configuration is for your GPU and breaks the computation up and stuff. So it saves you from they all have this thing where they save you from a lot of hassle, you know, because they try to figure out a good way to parallelize the code, and of course they do the automatic differentiation. So they all do similar things. Once you've learned one, it's pretty easy to migrate to another, I guess. Yeah. What do we got? Half an hour left. Okay, so let's just. Okay, so let me quit out of this, and we probably don't need this anymore. So let's just start to talk about the variations, and then some of this we'll have to get to next week. Okay. Okay, so these are some preliminaries about probability. Oh, wait a sec. So I mentioned that in order to understand these things, we need to know something about probability. So I'm just trying to summarize some of what's needed. So probability, originally probability was based on sort of gambling and discrete events. So you roll a six-sided die, there are 6 different outcomes which we consider to be equally likely. You toss a coin, there's 2 equally likely outcomes, and so on. You you spin a roulette wheel, and maybe there's 35 possible outcomes. So a lot of this is just kind of terminology. So we have a set omega of possible outcomes, and we assign a probability P of omega. If it's a finite set, we assign a probability P of omega to every omega in there. So it has to satisfy these properties. So every probability has to be non-negative. If we add them up, they have to add up to 1. So yeah, if it's a 6-sided die, then the probability of each individual outcome is 1/6. So these are called atomic events, and then we can define kind of compound events as unions of atomic events. So if we say what's the probability that if the numbers are 1, 2, 3, 4, 5, and 6, the probability that the number rolled is less than 4. That means it has to be 1, 2, or 3. So the probability of, so this is like a complex event, is the die roll is less than 4. The probability of that is the probability of 1 plus the probability of 2 plus the probability of 3, which is 1/6 plus 1, 6 plus 1/6, which is a half. The probability of the number being odd is also a half, because it's 1 or 3 or 5, right? And the probability of it being less than 3 would be 1/3, because it could only be 1 or 2, right? So we talk about random variables and probability distributions, okay? Now, probability, if we have different events, we can look at the probability of both things happening or neither of them happening, and we get these kind of Venn diagrams. So the probability of A or B happening is the probability of A plus the probability of B minus the probability of A and B, right? We add up these 2 circles and subtract off this bit in the middle, and there's a generalization of this to larger numbers of events. So if we had A, B, and C, we would say that the probability of A or B or C is equal to the probability of A plus the probability of B plus the probability of C minus the individual minus A, probability of A intersect B minus probability of A intersect C minus probability of B intersect C, but then we have to add on probability of A and B and C. Yeah. Now, often we have if we have continuous variables, then it doesn't really make sense to say the probability of something being exactly equal to a certain value. So let's say that we have a uniform variable distributed between 18 and 26. We draw this probability distribution as having, so that the total integral is 1. So the distance between here is 8. So the height is 0.125. The whole area is 1. But we don't really, if we pick some number in the middle like 20, we can't really say that the probability of the thing being exactly equal to 20 is 0.125. What we really mean is that what we really mean here is we're saying, well, we look at the probability of it being within a certain range of 20.5. You know, so we pick some little number dx and we say, well, what's the probability of x being between 20.5 and 20.5 plus dx? And we divide that number by dx, and that's what's equal to 0.125, right? So it's always about the probability of it being in a little range like this. And some people are surprised when they see a number bigger than 1 here. But if you had if you had number uniformly distributed between 18 and 18.5, then this number would be 2. Right, but it doesn't mean that the probability is equal to 2. The probability is always, you have to multiply by this dx in order to get an actual probability. Okay, so the most common probability distributions are this uniform one, and then the other one is this Gaussian distribution. Or sometimes called a normal curve or a bell-shaped curve. And this is a very important formula. So you should try to remember this. So this normal distribution, you have a mean mu. This is drawn as 0, but you have a mean mu and you have a standard deviation sigma. And the probability of x is equal to e to the minus x minus mu squared over 2 sigma squared. And then we have a normalizing constant out the front, which is 1 over sigma times square root of 2 pi, to make the whole thing have an area of 1. And this is very important because there's this thing called the central limit theorem or the law of large numbers, which says that if you have a lot of random numbers and add them all up, the sum of them all will eventually have this kind of shape. You know, so if I toss a coin 1,000 times and count the number of heads, you'll get this shape. And the same thing if you pick 1,000 people at random and measure their height or their weight, normally you'll get this kind of curve as well. You know, this is like a ubiquitous kind of curve. Okay, so where are we? Right, so what we discussed before is kind of the normal, the sort of plain vanilla backpropagation. Now, there's a few different variations of backpropagation. So I think we've only got time to discuss one of them today, and then we'll do the others next week. So we'll talk about cross entropy today and defer the others. Now, in each case, we have a sort of, there's sort of a hand-wavy kind of justification, and then there's like a mathematical justification. Okay, so cross entropy. Now, what we talked about before was the squared error function. We took the target value and we took the output of the network and the target value and took the difference and squared it. Now, for classification tasks, the output is, remember that for classification tasks, the target output is either 0 or 1. 1 means it's in the class and 0 means it isn't. Now, it turns out that for those classification tasks, it's often better to use this error function rather than the squared error function. Now, the reason is, let me try to draw a picture here. This is mainly an issue when you have asymmetric data. So 0 and 1. Let's suppose you're looking at financial fraud. You're looking at financial transactions. You've got a database of 10,000 financial transactions, and 100 of them involve some kind of fraud, where someone's using a credit card fraudulently or trying to steal money. So if you're trying to classify whether something's fraudulent or not, so let's say you have a network and you put in certain inputs, and then you're trying to output 1 if the thing's fraudulent and 0 otherwise. Well, you may have a situation where 99% of the cases are not fraud. So in 99% of cases, the output is 0, and in only 1% of cases, the output is 1. Now, if you use some squared error, there's a very high risk that the network will try to minimize the error by simply classifying everything as 0. 99% of the time, it's going to get the answer right. And the 1% of time, it gets the answer wrong. But this error function, if it's the squared error function, there's some fixed penalty that it's getting. Every time it outputs 0 when the answer should have been 1, there's some fixed penalty. And that's only happening 1% of the time. So the network may become lazy and say, well, I'll just wear that penalty. I don't care. I'll just classify everything as 0. So it may actually not give you any information. So in order to avoid this, we replace the error function with another error function that actually blows up to infinity as you go to 0. So if the correct answer is 1 and I'm predicting something close to 0, the error will increase. As I get closer and closer to 0, this error goes up to infinity. So this very heavily punishes the network for giving a wrong answer. So if we use this kind of error function, it forces... The network can't be lazy like this because the error would become infinite. So it forces the network to keep the values away from 0, and it forces it to try to make some effort to discriminate the data. It may still give a value close to 0 for everything, but it will separate out the inputs and it'll give a higher value for the ones that actually are fraudulent. It will give a higher value than the ones that aren't fraudulent. So you will get some discrimination there. Okay, so that's the kind of hand-wavy justification. And it turns out that a good choice of error function is actually this. Now, so how do we make sense of this? Well, if t is the target output, so if t is equal to 1, this term disappears and we're just getting minus log of z. So that function I just drew for you is actually minus log of z. Log of 1 is 0, and as z goes towards 0, minus log of z goes up to infinity. It goes slowly to infinity, but it does go to infinity. If the target value is 0, this term disappears, and you get minus log 1 minus z. So again, when z is 0, it's 0, and when z is 1, it logarithmically diverges to infinity. Now, and interestingly, when we replace, this looks a bit complicated, but actually in a way it simplifies the mathematics, because the derivative of this function actually cancels out the derivative of if the transfer function is the sigmoid, the derivative of this function actually cancels out the derivative of the sigmoid and makes the computations a bit easier. Okay, so now I'm going to tell you the mathematical justification for this. I got 5 minutes before the video stops. You know what? I think I'm going to leave this till next week. I don't want to try to cram this in. Okay, I'll leave you in suspense. So next week we'll talk about these variations, and then we'll start in on convolutional networks.
Can we use the GPU version of TensorFlow in VLab?
In VLab, it won't. No. In fact, it's very slow. Unfortunately. We couldn't. We can't get it to use. Unfortunately, we can't get it to use the GPUs on any of the lab machines. It's a frustration.
I read an article about why they use the cost entropy cost function because if we use the quadratic cost activation function, it always ended up like this and minus the whatever it is and times the activation function is derivative, and the derivative is like this in the sigmoid activation function. And if our target is 0 and in the initial state is 1, and it will be take a long time to converge when we initial in this point, because the deviation is very small in this place, and when we go through, when we converge in this, when we move to this way, it will be bigger, then we will be fast, and we will be slow again.
That's right. That's right.
Yeah.
So it's it's kind of related in a way to this thing about outliers.
Because if you use the activation function as the cost function is cost entropy, we will cancel out the derivative of that term, so it won't be affected by the derivative itself. So normally they come up with this cost function by using the integral of z minus that whatever it is of your output.
That's right. In some situations it may be a benefit because this outliers, if one point is really an outlier, eventually it'll just cut that point off and won't try to fit it at all. Whereas the cross entropy will try to fit everything. but depends on the situation.
And as you talked about earlier about the preprocessing of the data,
Yeah.
I want to know if the data is a string, how to represent it in a numerical way, like 0, 1, 2, 3, 4, 5. You have to do it by manually, or is there another way that the machine can help you do that?
If the data is what?
Yeah,
String?
string, but it
Text, you mean?
text, yeah.
Oh, pre-processing
Yeah,
text.
previous.
Oh, well, we'll talk about that later. But if it's sometimes they do it by word embeddings.
Yeah.
They assign a vector to each word.
Yes, but probably we don't. If we don't do it by hand, we don't know which word represent the much higher value or lower.
There are ways to assign word embeddings which try to put similar words near each other.
Okay, sure. Thanks.
I was wondering, last week you said that you are